So if we're interpreting the confidence level, okay, so the picture for confidence level looks like this. Here's my P. Here's my the value I'm attempting to estimate. Okay, and I'm going to go ahead and assume 95% confidence. Okay, and so we have all these different possible samples we could get, right? And so the basic idea is we say that this distance, for 95% confidence, by the way, that distance is 1.96 times the square root of p hat 1 minus p hat over n. Okay? And if I use that, so it's basically my critical value, 2 standard deviations, right? Okay? If I use that, any of my possible p hats inside those 2 boundaries, okay? Any of those, if those are my p hats, my interval will contain p, because those are the p hats that are close enough to that true value that if I use that as my margin, I'd be all set. But if I, for instance, picked this p hat here, and I used that distance, this distance, right? The actual value is coming straight down there is outside my interval. So when we interpret that confidence level, what we are essentially saying is what percent of the p hats of the possible samples are close enough to the true value that our interval will contain that true value. Now, they have a very specific interpretation for a large number of samples. "95% of the possible confidence intervals So I take a large number of samples and then I run a confidence interval for those samples. 95% of the intervals will contain the true value. And I'm going to kind of do that because that's something you would say in context. So like if I'm estimating what percent of people are going to vote for some sort of local issue, 95% of the intervals will contain the true proportion of people who would vote yes on that particular issue. Okay? All right, to interpret your p-value, for your p-value, what you do is you assume the null hypothesis is true, and then you say, could my sample have happened? So your p-value is the probability that the observed sample or more extreme could happen if that null hypothesis is true. So the first thing you're going to say is if blank. And then this you're going to describe the null hypothesis being true in context. Okay? Because if it's going to say interpret that p-value in context, that's the easiest way to get that context in the first place. All right, so if that null hypothesis is true, the probability that we could get a sample of, and then this is going to do blank, right? Like p hat equals whatever, or more extreme, is blank. And that's what you would fill in with your p-value. So there's some big ideas behind that. Your p-value is a probability, which means if you write your p-value as a value bigger than 1, it's an automatic I. If you refer to a p-value bigger than 1 in your conclusion, automatic I. Okay? So if you get a p-value bigger than 1, your what's going on is that your calculator gave you the p-value in scientific notation. Okay, your calculator, when you run those shortcuts, any of like the 1 prop z test, the 2 prop z tests, okay, any of those tests in your calculator, it will not give you a p-value bigger than 1. It'll say something like 1.13 blah 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 e negative 5. And you have to recognize that that p-value is in scientific notation. Yes, you can write it as times 10 to the negative 5th. Is that what your question was? Okay, that's not a problem whatsoever. Okay, but you do need to recognize that it gave it to you in scientific notation. I would write the scientific notation and then write approximately 0. Everybody good? Okay, so the other thing we had is some questions that are likely going to come up about the mechanics of these tests. Okay, so our margin of error is always plus or minus z. And if they're talking about sample size, it'll be the square root of p hat 1 minus p hat over n. Because they're not going to give you a sample size margin of error question when there's 2 samples, because that gets way too hairy, okay? All right. So the biggest piece is, like, first of all, as n increases, so as I increase my sample size, what happens to my margin of error? It's going to decrease. And the other way around, right? Okay? Now, every once in a while, they throw a really wonky thing in, and they'll say, like, let's say I multiply my sample size by 4. Is everybody with me? They're going to want to know what exactly happens to the margin of error. Do you guys get what I'm saying here? Okay, and what's happening is I throw that 4 right there. That's what would happen. Well, what do you got? So noticing that 4, are you guys with me that that's basically dividing by 4, but not, because that 4 is under it, the square root sign. So what's going to happen is if I multiply by my n by 4, my margin of error will be divided by the square root of that 4. And here's how I've seen it asked before, okay? They would say something like, they're doing an estimate, and that estimate yields the following interval, 0.25 plus or minus 0.08. If I look at this, I know for starters that my p hat is 0.25. Because that is, like, when we do that interval, it's the sample value plus or minus our margin, okay? And then they're going to say, they might tell us that the sample size was 100 for this interval, okay? And then they say, all right, but then we took a different one of sample size, let's say 400, okay? And they want to know what is the new margin of error. They never give you the confidence interval. They never give you anything, right? So the idea is, hey, I multiplied my sample size by 4, so my margin of error is going to get divided by 2, the square root of that 4. So basic premise is, if I'm multiplying my sample size, I'm decreasing my margin of error, and that sample size is under the square root. So my new margin of error would be 0.04. You guys, if I give you that the interval is 0.25 plus or minus 0.08, what's the interval? Can we go from 0.25 plus or minus 0.08 to be 0.17 and 0.33? Are you guys comfortable getting there? And then if I told you, well, let's not even worry about the rest of that. Okay. All right. So that's kind of just like recognizing how sample size influences our margin of error. That applies to confidence intervals because confidence intervals have a margin of error. Okay? Now, type 1, type 2 error, power, and alpha, those all apply to tests. Is everybody good? And so a type 1 error is the null is true. We reject the null. In other words, the null is true, but we're making a mistake. So we're like rejecting truth is a mistake, yes? Okay. Likewise, type 2, the alternative is true. We don't conclude the alternative. All right, so when we start a test, there's two possible starting points for our test. The null is true, or the alternative is true. Those are our starting points. And we don't get to know which of these branches we're on, but these are our two possible starting points for a test. Okay? And then from there, we run our test and we have two possible conclusions about the null. We reject or we fail to reject. All right, so if the null is true, but I reject the null, as we just said, that is a type 1 error. If the null is true and I fail to reject the null, I am making the correct decision. All right, if the null is true and I reject the null, good decision or bad decision? I'm sorry, if the alternative is true and I reject the null, I'm going to conclude that the alternative is true. So, in that case, that is a correct decision. Failing to reject the null, this would be a type 2 error. We still good? Okay. All right, now, how does power and alpha connect in? Okay, so I'm going to start with alpha. Alpha ends up being the probability I make a type 1 error. So like here is alpha. And to kind of think through that, let's go back to this picture. Let's go ahead and say my null hypothesis is going to be p equals 0.2, and my alternative hypothesis is p is greater than 0.2. And so what's going to happen is if I'm going to reject my null, well, this is a one-sided test. It would be shaded to the right. And what that means is that if my p hat is in this area, my p-value will be less than alpha, and I will reject the null. And if my p hat was over here or over here, my p-value would be bigger than alpha, and I would fail to reject the null. Okay? And in this picture, rejecting the null, because remember, this is where the null is true, rejecting the null is making a type 1 error. So the probability I make a type 1 error is whatever this area is going to be, which is my alpha in the first place. Okay? So alpha is your probability of making a type 1 error. All right? Now, if the alternative is true, it's a totally different picture because my center wouldn't be 0.2, it would be some version of p bigger than 0.2. Okay? And so from there, rejecting the null still goes with alpha. Rejecting the null is what we call the power of the test. So, increasing alpha, like notice that both alpha and power go together on my tree diagram here, yeah? Okay, both of them go with rejecting the null. The question is whether it's a good decision to reject the null or not. So if I want to decide increased power, I want to decide am I more likely to reject or not. Okay? So to increase power, you can increase alpha, because these two things are the same probability, so increasing alpha increases power. If this is 10%, now this gets bigger, right? And all right, now, the other thing that's worth noting is if I call this the probability of a type 2, is that power and the probability of a type 2, they always equal 1. If you add the two of those things together, they should always equal 1. They're complements of each other. There is no name for here. It's the only one that doesn't have a name. Okay? All right. Increasing sample size increases the probability you make the right decision. Right? In general, if your sample size is larger, assuming that you have a well-designed sampling design, okay? So as n increases, power increases. Because you're more likely to be making correct decision. Okay? Okay, lastly, the only other way I might ask you about this, let's go back to these hypotheses real quick. Let's say you have to decide which would have more power, the actual p being 0.25 or the actual p equaling 0.30. Which one of those truths makes me more likely to reject my null hypothesis up here? Well, this one is further away, right? It is, if the actual p is 0.3, my sample is going to way more likely to make me reject the null than if the actual p is 0.25. Okay? So you'll always be given like some version of the alternative hypothesis when you're talking about power. The power to detect p equals 0.3 is higher than the power to detect p equals 0.25. Because if this is the actual truth, the probability you're getting one of those lower p hats is smaller. Because your p hats are all going to circle around that 0.3 in the first place. All right. I'm done here.